What we'd like to do now is take a look at what effect having carbon-carbon double bonds in the structure of the fatty acid has on the melting point of that fatty acid. You already know that some fatty acids have no double bonds, like this one, 0. This is saturated. Oleic acid has 1 carbon-carbon double bond. That's a monounsaturated. Linoleic and linolenic acid are both polyunsaturated, 2 carbon-carbon double bonds and 3 carbon-carbon double bonds in the chain. Now in this notation I'm showing you a structure that helps you see a little bit better what the shape of the molecule is. We cannot see the carbon-carbon double bonds, but you know they're there because of this notation. Check out what the carbon-carbon double bond does to the shape. Stearic acid has no double bonds, carbon-carbon double bonds, and its overall shape is pretty straight. It zigs and zags like this. We know that from the line angle notation. But as a whole, when you consider the shapes of the atoms themselves, it's a pretty straight molecule. Look what happens though when you add a double bond right there. There's a bend or kind of a kink in the molecule. 2 carbon-carbon double bonds, it's bent even more. 3 carbon-carbon double bonds, it's bent even more. So we want to think about how that affects the melting point. We do this step by step. First, I ask how many, which fatty acid has more carbon-carbon double bonds, stearic or linolenic? Definitely linolenic, right? 3 carbon-carbon double bonds compared to 0. Linolenic has more carbon-carbon double bonds. It's polyunsaturated. What does that do to the shape? It bends it. The more double bonds you have, the more bent it gets. So now, think about how that affects how closely the molecules can pack together. We've been talking about how packing together determines melting point. When they're straighter, they can get closer together. You would have an easier time packing a box full of these molecules that can line up nicely compared to these that will get all tangled up and they can't overlap so nicely. So the straight ones are closer together. What does that do to the intermolecular attractions, forces between the molecules? Well, when the molecules can get close together, like they can here, those will make those intermolecular attractions, intermolecular forces, stronger. There can be more overlap, more touching. And then we can say, well, when those forces, attractions are stronger, what does that do to the melting point? Will it be higher or lower? If the attractions between those two molecules, any two molecules, are stronger, that'll make for a higher melting point. It's harder to pull them apart if the attractions are strong. And if the melting point is higher, it's more likely to be a solid. It's hard to pull those molecules apart. You have to add more energy, you have to heat it more, and so it's more likely at a given temperature to be a solid. So we could predict which should have a higher melting point, stearic acid with no carbon-carbon double bonds, or linolenic acid that has 3 carbon-carbon double bonds, and we're going to predict for higher melting point, we'll predict stearic. Stearic acid we predict has a higher melting point because it has 0 carbon-carbon double bonds. Linolenic acid has 3 carbon-carbon double bonds. This is more likely to be a solid. Stearic acid is more likely to be a solid than linolenic acid. We can summarize that this way. There's 2 things we'll say. Here's the first one. As the number of carbon-carbon double bonds goes up, the melting point will go down. We saw that. The melting point goes down when you have more carbon-carbon double bonds. That's the first trend we can notice. But we can also predict, based on what we already know, we can predict this. As the number of carbons in the chain goes up, not the number of double bonds, but the number of carbons. Here they're all 18, but we can see examples where the number of carbons are different. What does that do to the melting point? Well, more carbons makes for a longer chain. There will definitely be better overlap, more overlap, interaction between longer chains than shorter chains. So, as the number of carbons goes up and the chain is longer, the melting point will also go up. Fatty acids with more carbons will have a higher melting point. Fatty acids with more carbon-carbon double bonds will have a lower melting point. What we want to do then is take a look at comparing melting points of different fatty acids. Let's do that. Let's see here. Let's compare a few. Let's compare these. I'll look at this first. 16.0 and 16.2. 16.0 and 16.2. They both have the same number of carbons, but this one has 0 double bonds. This one has 2 carbon-carbon double bonds. This will have a higher melting because it has fewer carbon-carbon double bonds. Higher melting will happen when there are fewer carbon-carbon double bonds. On the next example, both the number of double bonds is changing and the number of carbons is changing. This second example has fewer carbons. That will make for a lower melting point. It has more carbon-carbon double bonds. That will also make for a lower melting point. So if we want to think which one will have a higher melting point, it will be this, because it has more carbons, fewer double bonds. Same thing here. If we look at this second one, this has, let's see, this has more carbons. More carbons is higher melting. 0 carbon-carbon double bonds compared to 4. So this has fewer carbon-carbon double bonds. Fewer carbon-carbon double bonds is higher melting. So I would say that this second one has a higher melting point. Now sometimes the two factors will work against each other. You could have a fatty acid that has more carbons and more carbon-carbon double bonds. We won't try to make those predictions. We'll do examples like we've just seen. The final one that we want to take a look at, we'll be looking at how these happen later, but for right now we'll just look at the shape. This fatty acid right here has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 carbons, 1 double bond. How about this one? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 1 double bond. We would predict that this has a higher melting point because it has more carbons. So we already can predict that this will be higher melting. But also what you want to start noticing is this. This double bond here is trans. This is a trans double bond. This bond here is cis. And we will see later, just kind of getting a sneak preview right now, we'll see later that the trans double bond straightens the molecule back out. This molecule is pretty straight compared to the bent cis. So it's higher melting for sure because of more carbons, but also because the trans configuration of that double bond has straightened the molecule back out. So we've made some sense of melting points of fatty acids. What we want to do next time is look at reactions of the fatty acids. That's coming next.